Alright guys, so we are doing Deutsch-Jozsa's algorithm today, which is a sort of expanded or modified version of Deutsch's algorithm from yesterday. Now, what Deutsch's algorithm did was that we had an input, or sorry, we had a function f, which took an input 0 or 1, and it popped out an output 0 or 1. And if the output was the same for both inputs, we said that the constant was, or that the function was constant. And if it popped out one result for half of the inputs and a different result for the other half, we said that the function was balanced. And so Deutsch's problem was, well, it's asking ourselves, is the function constant or balanced? And we saw that while a classical computer would need to perform two queries to figure out if if the function is constant or balanced, um, Deutsch's algorithm found that quantum computers only need one. So that was it was a demonstrated improvement that quantum computers can be faster than classical computers. Now, Deutsch-Jozsa's algorithm is slightly different, but still very much the same. It basically says for an input of any length, which is obviously a bit input, which pops out a value 0 or 1. Is the function constant or balanced? So that would mean that the function takes in many different or all permutations of zeros and ones of n length, and it spits out either the same answer for all of them, so 0 or 1, or it spits out 0 for half of them and 1 for the other half. But it doesn't have to be in order. It could be that, some, like it switches back and forth between the output being 0 and 1, etc. So obviously then, if we sort of consider the worst case scenario for the classical computer's case, it would need to query half the inputs plus 1. And that's because in the worst case scenario, all the outputs are the same because, or up until you reach the halfway point, because coincidentally the outputs are like ordered in that way. However, once you calculate the half plus one bit, whether it changes or not in the worst case scenario determines whether or not it's constant or balanced. Now, and this is where it gets a little impressive, quantum computers only need one query, and we'll see why now. So, the way that this is queried is by Deutsch-Jozsa's algorithm, which is the one we see right here, and it's very much reminiscent of the one we saw yesterday. It's just an expansion, in fact. So, we have a starting sort of register of lots of qubits in the zero state. Now this icon right here just means that we have like many, or we have n um, qubits in the state 0 tensored together. And then at the very end, they're also tensored to a minus state right here. That's the same meaning as this slash right here. It just means that we don't feel like writing out like every single line like this, because what if there's like 1,000 qubits? This sort of just simplifies it to, okay, we have n many qubits represented by this string because we perform the same action on them anyways, so we can generalize without losing information. And then of course this state is unique relative to that, so we do need to keep it down here. Anyways, um, if we look at state psi1, which has us perform a Hadamard on every one of these qubits, except for the, what's it called? The minus state. Um, we see that it has this effect of basically producing an equal superposition of every possible bit string of length n. And that's because you sort of just have an equal superposition of 0 plus 1 multiplied by 0 plus 1 multiplied by 0 plus 1. And so you get a permutation of every bit string of length n of 0 and 1. So if it's 3, if you have length 3, for example, you would get 0, 0, 0, 0, 0, 1, 0, 1, 0, etc. up to the eighth one, which I don't know what number it represents in bits. I guess it would be the number 8 or the number 7, maybe, because 0, 0, 0 represents number 0, I guess. But yeah, um, then we look at ket, or state psi2. Now here, we have performed our unitary transformation on the system. Now this unitary transformation basically just corresponds to the function that it is that we're investigating. Now, notice that it is performed on our quantum system, which allows us to linearly distribute it into every term. And that allows us to write it up in this phase oracle form, which is actually the same one we saw yesterday. So you might actually notice that because it's a very similar problem, we're using some very similar tools and methods to figure out the problem. Now, basically what the phase oracle form said was that if you have a unitary transformation, or a unitary operation of this form, where you have a variable for this ket, and you have the minus sign, or the minus net, what's called minus state for this ket, then you could express the unitary transformation as a -1 to the power of the function's value. So if we do that, we get this expression that we're seeing right here. Now, um, once you're done with that, you then perform another Hadamard right here, basically just undoing this right here after our unitary transformation. But now we can't actually use the same sort of identity that we did over here because we don't have an equal distribution of every possible bit string, meaning now we have to get creative. So instead, we actually use this identity right here, which is that if you now perform a series of Hadamards on your register, you instead get another sort of sum that you can express via another parameter called z. Now I'm going to be honest, uh, there's a lot of math behind this expression, and by a lot I don't mean like pages, but like you can find material online which demonstrates how you get from this to this online. It's just that it takes a lot of time to write out, and I'm writing this with my mouse, so like it already takes a lot of time and it hurts my wrist. But trust me, is what I'm trying to say, that we can rewrite the expression we have for psi3 using this identity right here, which allows us to re-express the state psi3 like this, where we have a sum over z summing over the sum over x for the state z, where we have the amplitude shaped like this. And this here is just supposed to be a dot product between x and z. I forgot to mention that. But we still have this aspect which we recognize from up here. Anyways, um, now I'll admit there's also a lot of math behind why the result comes out like this, which I also didn't bother writing out. But basically the way that this equation behaves is that if f is constant, the way that these multiplications or like these powers work out is that they end up being um, forming either 0 or 1, or sorry, plus 1 or minus 1. Um, Excuse me for a second, I forgot to mention that what it is that we're actually doing here at the end is that we're actually only measuring the state amplitude corresponding to the state 0, 0, 0, etc. And you can actually distinguish whether or not the function is constant or, oh my god, what a typo. Excuse me for a second. This function distinguishes whether the function f is constant or balanced by measuring the amplitude corresponding to the ket 0, 0, 0, 0, 0, etc. Because when you measure this state, if you get a value for the amplitude of either plus or minus 1, that means that the function is constant. And if you get an amplitude value corresponding to 0, it means that it is balanced. Basically, whether you measure it or not, which is a guarantee, distinguishes between whether it's constant or balanced. And notice that this only requires just a single measurement, which is why we say that this algorithm only needs to be queried once to determine whether or not the function f is constant or balanced, as opposed to the half plus one queries that we would need for a classical computer. I hope this made sense, and thank you for watching. Take care.